So Chung, you're ready to go?
Yeah.
It's my great pleasure to introduce Ngo Viet Trung of the Vietnam Academy of Science and Technology, and he will speak on regularity functions of graded ideals.
So thank you. It is a honor for me to give a talk at the seminar Fellowship of the Ring, and the the topic of my talk came from a joint paper of me with Hoa Hợp Nguyen, and which already we posted already in its archive. And let me first recall some basic notion, maybe about regularity. I couldn't get it. Sorry, I can. Yeah, now it's okay. So let me first fix some notion. So my setting is a standard grade algebra A of a field. And if we have an Artinian module H, N, N, then I denote by An the large non-vanishing degree of N. And if N is 0, then I define N is minus infinity. It's just some convention. Oh, it's too long. It takes too long to move. Sorry. Now it's okay. So now we consider a finitely generated grade A module M. Then the local homology module of M is also graded. And then I define the regularity M inches away, that it is the maximum of the vanishing degree of the local homology module plus some shift. But most of the people know regularity via the graded free resolution of M. So if we consider a graded minimum free resolution of M, then we know that the summon the component F, they are a direct product of grade free module, and so with some shifting degree. So I denote by BM the maximum degree of the free component of Fi. Then we can define the regularity in other way as the maximum of this BM minus I for I running from 1 to R, where R is the length of the free resolution. So now I will go to the subject of my talk. Then first of all, I will assume that I is a non-grade is a graded non-nilpotent ideal of R, because that here I consider the regularity of the power of I of the ideal I. So if I is nilpotent, then the power of I vanish or disappear for large N. So I will avoid this case for technical reason. So long time ago, then you and me and independently Korea Lam, and later on Chung and Wang, we proved that the regularity of the power of I is a linear, it's asymptotically a linear function. Now the slope of this function is can be defined, but can be computed. And it is a large, it is a smaller number, such as in plus 1 is equal to I small d. That is the idea changed by the element of degree less than d time in. Or in other words, we can consider we can replace I in degree less than d is a reduction of I. And this number, this slope, this number d is called the asymptotic degree of I. And I should mention that the first two papers of Kutkowski has open mind, and Kudilan, we consider only the case where the base ring is a polynomial ring. And the proof is it rely on the bicarated minimal free resolution of IM. But in the paper by in the joint paper with Wang, then we have to develop another method to prove this asymptotic linearity, because that we don't have the we don't have the minimal free resolution in this case. So if no otherwise specified, I will assume that I is equigenerated. That means I is generated in a single degree. And in this case, this degree is also the asymptotic degree. And now I define, I can consider now the difference between the regularity of I to n minus dn.
Chung, excuse me for interrupting, but we only see one slide here, your first slide. Is that correct, or?
Oh, really?
Yeah, well, it just says it's that first slide where it says regularity functions at the top, and it's page 1 of your somehow. I mean, if you can't get so it's not advancing, I guess.
We see a short
Yes,
on the bottom.
I realize it's a sort of slow. It moved very slow from. Here in my screen, I can still in my sharing screen, I still see all the what I talk about.
What page are you in on your manuscript? That it says page 1 to 53.
Now I have now I moved already to page 1.
Okay.
Page 2.
Page 2. Okay, so right now we're seeing page 1.
That is bad. So let me maybe now because I use full screen now, maybe I move to the normal PDF screen. Let me fix the problem. Fine.
Yeah, there's
If I
one sentence.
If I move
there are 3 sentences.
Yeah, okay. So let me go now to the full screen.
Wonder if the full screen
Can
is
you see?
working.
Yeah, if that's what's causing the trouble, yeah.
Maybe it's
Yeah, okay, I will go back to, I will start, now we start again with the second page. So let me recall the definition of the regularity. And I need some convention here. So my setting is a standard graded algebra A over field. And if we are given an Artinian module n, then I will denote by an the large non-vanishing degree of n with the convention that an is minus infinity if n equal to 0. So Now let M be a finitely generated A module, then grade module, then the local homology module of M is also graded. So I can consider the maximal non-vanishing degree of every local homology module, and I define the regularity as the maximum gives a non-vanishing degree plus a shift. And if A is a polynomial ring, then we can also define the regularity by the minimal free resolution. So if I denote by Bm the maximum degree of the free component of Fi in the minimal free resolution, then the regularity is just the maximum of Bim minus I. Now I move to screen 3. So
Good,
this
we
is
see it.
the topic of my talk. Can you see it?
Yeah, it's on 3. It's working.
Yeah. So the topic of my talk is about the asymptotic behavior of the regularity. So for that, I have to consider the power of graded ideal I of A, and I have to assume that this ideal is non-nipotent. This is very important because that if I is nipotent, then the power of I is vanished for large n. And so we have no function regulative In. A long time ago, we proved that the regulative of the power of n is asymptotically a linear function. And moreover, we can compute the slope of this function. And in this case, the slope is a smaller number, such as In plus 1 is equal to the ideal I generated by degree less by the element of degree less than d, less or equal to d times In. In fact, that here we can say that we can reply I in degree less than d by any minimal reduction of I, graded reduction of I. And this degree, this slope is called the asymptotic degree of I. So I should also mention that in the first 2 papers by Koskubsky, Herzog, and Chung, and by Kodia, and independently Kodialam, then we proved this research only for polynomial idea. And in this case, we can use a minimal the bigrade minimal free resolution. But if the base ring is not a polynomial ring, then we have to develop another method to prove this result. So now I will assume that the root out of this paper, I will assume that I is equigenerated. That means I is generated in a single degree, and this degree is also the asymptotic degree of I. And then we can define we can define En is the difference of the regularity of I to n minus dn. And by this asymptotic linearity of the function rate of In, then this sequence of different En is a convergent sequence. And this function, this sequence was studied first by Eisenberg, Harris, and by 2 papers by Eisenberg and Harris, and by Eisenberg and Ulrich. And later on, it is named the regularity defect sequence by Bellecamp. Now, in the paper by Eisenberg and Harris, And by Eisenberg and Ulrich, then they consider what is the case where the dimension of the ideal is equal to 0. As you can see that this is the most simple case, the simplest case, because that we assume that the ideal I is equigenerated and I is an M primary idea. And Eisenberg and Harris, they prove that this sequence En or this recurrent defect sequence is a weakly decreasing sequence of non-negative integer. So there are two facts here. First, that it weakly decreases, and the second fact that they are non-negative integer. And later on, Eisenberg and Ulrich, they prove that if the zero local homology module of A vanish, then, for example, if A is a polynomial ring, then the difference between En minus En plus 1 is less than or equal to D, the asymptotic degree. And there are a few other reasons, but I mentioned here only that they couldn't understand this sequence all. For example, they raise the question whether the difference between En minus En plus 1 is always weakly increasing. And I would like also to mention that if the ideal I is not equigenerated, then the sequence En can go going up and going down. In other words, they can fluctuate. Now we came to the case where the dimension of I is bigger or equal to 1. Then it is really hard to find example with En less than En plus 1 for some n. So that means that it is increasing at some place. And the first example where we have E1 less than E2 is given by Stormfest long time ago. And later on, or maybe at the same time, Konka gave example where the regular this defect sequence jump at any place. And I would like also to remark that this example by Stormfeld and Kolka, they are polynomial ideas. And this is much more difficult to construct example in the polynomial case. And especially in this case, En equal to 0 means that In had linear resolution. Now I would like to say that usually that the behavior of the function regularity of I to n can be deduced from that of the function of regularity of A mod In. And this can be done by considering the short exact sequence. This short exact sequence. But we don't have a precise formula for the relationship between the regularity of In and the regularity of A mod In. But it has some advantage because if the dimension of the ideal equal to 0, then the regularity of A mod In it's just the maximum of the power t, such that m to the t is not contained in In. In other words, this is the largest non-vanishing degree of the ring A mod In. And we all know that if A is a polynomial ring, then the regularity of I to n is equal to the regularity of I mod in plus 1. So in the polynomial case that we can move from the power in to the quotient ring A mod in. And in my opinion, that to study the function of A mod of the regularity of A mod in, then we should first study the function of the regularity of in mod in plus 1. And it can be done by this short exact sequence. But we cannot, also we don't have any precise formula which link the regularity of the quotient ring A mod in to the quotient module in minus in plus 1. So now I want to describe the basic property of the function, the regularity of in plus minus 1 mod in. So now I assume that I is an arbitrary gradient, which is not necessarily equigenerated. Then the regularity of in minus 1 mod in is equal to dn plus e minus 1 for large n, where d and e are the slope and the intercept of the asymptotic function regularity of in. So d in this case is just the asymptotic degree of I as defined before, and e is the same. And this this proposal can be easily proved using the fact that the regularity of in is asymptotic is equal to dn plus e for large n. We just use some short exact sequence and you can see immediately. And the second property of this function regularity of in minus 1 mod in, it's just that it is always bigger than dn minus 1 for all n bigger than 1. The proof of this result need we need a little trick. I don't want to recall the proof here, but it is not so difficult to prove it. So we don't, but for this property was the second property, I had to assume that the h of the ideal R is bigger than 0, and we do not know whether this property still holds if the height is equal to 0. Now, just like in the case before, I consider the difference between the regularity of this quotient module minus dn plus 1. So just remember that the regularity of this quotient module is equal to dn plus e minus 1. So I take out dn minus 1. So we have to consider this sequence Cn. And then by the first proposition, then Cn is convergent. This sequence is convergent. And by the second proposition, then this sequence is they are all non-negative integer. And we also call this sequence Cn the defect sequence of the function regularity of in minus 1 mod in. Now I will go to our main research concerning this function. We can prove that in the case where the dimension I equal to 0, then a given sequence of non-negative integer is a defect sequence of the function of this function, even only if it is quickly increasing. Of course, that we we prove it for equigenerated ideal. And the weakly for the necessary parts to prove that it is weakly decreasing, that we just use the fact that the defect sequence of the regularity of IN is also weakly decreasing, which had already proved by Eisenberg and Harris, and then we use this short exact sequence to prove this the necessary part. So this part is easy, but for the sufficient parts, that we have to construct some example of great ideal I with a given defect sequence. And this is the main part of the proof, and I will speak about that later. And the second theorem in the second main result on this function is concerns the case where the dimension of the ideal I is bigger or equal to 1. And in this case that we can prove that that the sequence of non-negative integer is a defect sequence if only it is convergent. So these results are rather surprising, because that we can keep a complete description of the function regularity of the quotient module IN minus 1 mod IN. So for the second theorem can be also reformulated in terms of the numerical function Fn. So a numerical function Fn is a defect sequence of the function of this function regularity of IN minus 1 mod IN. If and only if Fn is asymptotically linear and Fn is bigger or equal to Dn minus 1 for all n bigger or equal to 1. So conversion here means that it is asymptotic linear, and non-negative integer here correspond to this condition Fn bigger or equal to Dn minus 1. So for this second theorem, we only need to prove the sufficient part. That means we have to construct I with a given defect sequence Cn. So now I go on to show how to construct such an ideal I. So let me first describe the idea. So for a long time that I consider the problem of describing the function, the regularity function, is very difficult. But then we realize that it can be we can simplify the construction of ideal I with a given defect sequence. So the idea is that the first let we first consider the associated great ring of I. And then if R is the number of generator of I, then I can consider a polynomial ring A wide over the base ring A in A variable. And then we have a presentation of the associated ring Gi as a quotient ring of this polynomial ring by a graded ion Q. And then we have this isomorphy between the quotient module and this module. And that means that we can pass from the ideal I in the base ring A to the ring to this quotient ring of the polynomial ring over A mod Q. Then so in general, then I will construct a standard grade ring 8 of the form S mod Q, where S is a polynomial ring over a field in two sets of variables. So which corresponding to the bicarated structure of GI before. And then I will construct a graded aligned Q, which depend on the given sequence, defect sequence Cn. And then I replace I by this ideal I to D plus Q mod Q. So the power D here just to guarantee that the ideal I is changed by element of degree D. And then I will prove that this given sequence Cn is the defect sequence of this function. So this is the idea. Actually, that you don't need to put here to consider the power of I mod B here. If we can prove it for the k equal to 1, then we still have this kind of isomorphy, and we can say that we can deduce that the CN is still the defect sequence of the function of this regulative function. So if someone do not understand what I say, then please just raise your question. And now I consider the construction for the K where the dimension of the ideal is equal to 0. So we are given a weakly decreasing sequence of positive integer. And D is a number bigger than equal to 1. And then because that it is weakly decreasing, then there is a minimum integer M. Let's just Cn equal to Cm for n larger M. So this is a place where this sequence become stationary. And now let S just a polynomial ring in two variables, x and y over a field K. And then I define Q in such a way. So it's just a polynomial, it's just a monomial idea, very simple monomial in two variables. And then I define A as S mod Q, and I is the sum of ID and Q mod Q. Then I can prove that for all n bigger equal to 0, then the regulative function has this form for all n. And the proof here is quite simple. That we have this quotient module. It just you can rewrite in this case in this form, and that you can pass it to this quotient ring with some shifting degree, with some shifted degree. And then just looking at Q, then we can see that if n is less than m, then this ideal which appear here is just the ideal shaded by x2cn and id. And if n bigger than or equal to m, then this ideal is generated by x2cm and id. So they are completer intersection. And in this case, that the regulativity can be computed, and that gives you this formula. So it's quite easy in this case. And it's really surprising easy. And based on this construction, then we got the sufficient part of this theorem. This is the main characterization of this function, of this regulative function, in the case where the dimension is equal to 0. So for the for the characterization of the regulative function, the regulative function in minus mod in plus 1, I have to give another construction, which is more complicated. So again, that we are given, now we are given a convergence sequence of positive integer, which needing to be weakly increasing. And then let M be the stability index of its sequence Cn. And then I consider a polynomial ring in n plus 2 variable. And then I define P is the ideal shaded by the variable y, 1 to ym. And then I define Q in such a way, which is a bit complicated, but it's still a monomial idea. And then I let the basing A to be the positioning at mod Q, and I is this idea. Then this idea is equationated in degree D. Then I have this formula for this regulative function. And here that we have to move we have to move the index a little bit, because that usually that as before that I consider the sequence Cn starting from n bigger equal to 1. But here because that here I consider this module mod in plus 1, so I raise the index, I lower the index here by 1. So we have to consider a sequence, a conversion sequence starting from n bigger equal to 0. And I don't want to say about the proof of this construction, because that it is technically it's very complicated. I think that it go about 2 pages. And then from this formula, you can prove you have an idea of dimension 1. So in this case, we can see that the dimension of this idea I is equal to 1. And then it has this regulative function has the right formula. But for it, but we can also extend the construction to any higher dimension of I, just by adding new indeterminate to A. So that's why we can formulate the theorem for any given dimension of I. Now I will move to the description of the function of the regulativity of A mod In, so of the Gaussian ring. So we have some basic property. The first property is that we can prove that this function is again asymptotically linear, and it has this form, that the regulativity of A mod In is equal to dn plus e minus 1, and where d and e are the slope and the intercept of the function of the regulativity of In. And this can be proven very easily using this short exact sequence. That we know that the regulativity of I is asymptotic linear, and the regulativity of R is just a constant. So we can deduce from that fact that the regulativity of A mod In is also asymptotic linear. And the second result is just that the regulativity of A mod In is bigger or equal to dn minus 1 for all n plus or equal to 1. And this holds for any dimension. I say that because that in the case where the dimension of I is equal to 0, then this property of this regulative function was already proven by Eisenberg and Ulrich. But here we prove it for any dimension. Now again, I consider the difference between the regularity of A mod IN minus DN plus 1. So just remember that the regularity of the question module, question ring, it's just DN plus E minus 1. So I just take out the part where it is not user. Say. So now according to these two propositions, then this sequence AN is convergent. So by the first proposition and by the second proposition, then they are all non-negative integer. And then again I call this sequence AN the defect sequence of the function, right, of A mod IN. And now again the problem now is how to characterize the defect sequence of this regulating function. And for that we obtain a completed description of this regulating function for the zero-dimensional case. And this series says that if you are given a sequence of non-negative integer AN, then it is the defect sequence of this regulating function for an equigenetic ideal I in degree D with the width dimension equal to 0 if only if it is weakly decreasing and the difference between AN minus AN plus 1 is less than equal to D for all n bigger than 1. So it consists of two conditions. First of all, that it is weakly decreasing, and the second condition is that this difference is less than equal to the asymptotic degree. And the proof is not so hard. Then it follows from the first of all from the characterization of the function rect EIN mod IN plus 1. And then we have to consider this short exact sequence using some kind of inductive method. And here the condition that the difference between AN minus AN plus 1 is less than D. It's just equivalent to the condition that the regularity of A mod IN is less than equal to the regularity of A mod IN plus 1. And then because the regularity of this quotient ring is given by the large non-vanishing degree, then it is we always have this inequality, and that would imply that we have this condition AN, that the difference between AN minus the difference AN minus AN plus 1 is less than equal to D. So this fact is easy just from this from the computation of the regularity of the quotient ring by a zero-dimensional idea. And here I have to remark that this theorem doesn't hold if the base ring A is a polynomial ring. In fact, Bellingham, he already showed that in this case, then the regularity of I is always less than regularity of I plus 1 for all n bigger than equal to 1. And because that the ring A is polynomial ring, then we have that the regularity of function of the quotient ring is just also increasing in this case. And with, as I mentioned before, that this would imply that this difference is less than D. So because that here we have is strictly less, then this result cannot hold for the case of polynomial idea. And for the case where the dimension of the ideal is larger than 1, then I cannot give a complete description of the function of this regulative function. I can only give some kind some sufficient condition for the defect sequence. So this research says that the defect sequence of this regulative function for an equigenerated ideal D with the dimension is bigger equal to 1 can be any convergence sequence of non-negative integer an, and with the property that an minus an plus 1 less than equal to D. And this theorem can be also reformulated in such a way in terms of this regulative function, that the regulative function of the quotient module of the quotient ring can be any numerical asymptotically linear function, and this function should has to satisfy this property that fn is bigger than dn minus 1, and moreover it should be also weakly increasing. And the proof for this theorem use some construction which is similar to construction 2, to the construction 2 what I have mentioned before. And in this case that the base ring A has this form. It is a quotient ring of a polynomial ring over a graded ideal. So the polynomial ring had 2 sets of variables, and the ideal I had this form. So this proof is also very complicated. Here in this theorem that we require that this numerical function fn it must satisfy this inequality for all n, and it should be moreover that it's weakly increasing. And there are examples for which the regulative function is not weakly increasing. This was given by Nguyen and Vu in some paper, which is which already appeared before our work. Because we cannot have a complete description of this regulative function, so I raise this conjecture that this regulative function can be any numerical asymptotically linear function fn bigger equal to dn minus 1. So these are two functions we have proved already before, and the question here is whether it is also sufficient for the function fn to be the regulative function of this quotient ring. And I believe that it is true, because that when we consider the regulative function of in mod in minus in mod in plus 1, then we don't need any more conditions than these condition. Okay. But we cannot solve this problem. Actually, that our our construction doesn't work. Doesn't work at all. We try many times to use construction to prove this conjecture, but it doesn't work. And now I came to the characterization of the function of the regulative function of In. So this is our main aim as a beginning. In this case, we can also keep only a sufficient condition for the defect sequence of the function of the regulative function of In. That we can show that any weakly decreasing sequence En of non-negative integer with the property En minus En plus 1 bigger or equal to D for n less than m, where m here is a stability index of the sequence En, then this would be which will be a defect sequence of this regulative function. We can also formulate this theorem in other way, directly in terms of the regulative function. That we say that the function, this regulative function, can be any numerical asymptotic linear function Fn because even to the n that quickly decrease till it become linear. So we know that it will become linear, but we require that this function it quickly decrease. We also know that before that Fn is always bigger than Dn. And the proof here is not so difficult. It's based on the construction of one for the zero dimension K, where A and I have this form. And now I recall the question of Eisenberg and Ulrich, that they say that the different En minus En plus 1 should be weakly decreasing too. But in this theorem, that we only need that this difference is bigger than equal to D for n less than m, and that means that this difference can fluctuate, and then we can construct a lot of examples based on this construction. We can construct a lot of counter exam to the question of Eisenberg Ulrich. I have to say that I want to solve this condition. First of all, that my impression that it shouldn't be true, and I want to construct counter exam, and it takes me more than, I think that 15 years, more or less 15 years until we got his counter exam. Now again, that this research doesn't hold for polynomial idea, because that we have to assume here that this difference is bigger equal to D. But by a research of Pellicam, then for polynomial idea, then the difference must be less than D, strictly less than D. So we can see from this research that the general case upgraded idea and the polynomial graded idea, they are completely different. And now I want to conclude my talk with some open problem on the function on this regulative function reg of In. The first conjecture that we conjecture that a sequence of non-negative integer En is a defect sequence of this regulative function in the case where I is equigenerated and the ideal is zero dimensional, or the dimension is bigger than 1. If and only if that this sequence En is weakly decreasing That is for the case where the dimension for the zero dimension case, or it is convergent in the general case. And the second problem is to characterize the function rect in for polynomial idea. As I said before, that the polynomial case is very difficult. You can see from the example of Sturmfeld and Kolka that they just want to have some jump of the regularity, and they exam it very difficult. Actually, that we have some initial result in the polynomial case by using different methods than that in this talk, and that will be the topic of another paper, which is forthcoming. Okay, I will stop my talk here. My plan is to say something more about the saturation degree of created idea, but I have no time to tell more about the research about the saturation degree. So thank you for your attention.
Oh, thank you. Let's thank Chung for the talk. Wonderful talk. Does anyone have any questions? I'm not seeing, is anybody trying to say anything? Actually, I have a question. I'm actually curious about what you're saying about the saturation degree. Maybe you could you quickly tell us a little bit about what sort of problems you're working on?
I have some slide here. Yeah. So I move. So that the saturation degree is defined in such a way. It's just a large non-vanishing degree of the quotient between the saturation of the I and I. And we that it is some kind of generalization of the a weaker version of the inequality, because that if this quotient module is just the zero local homology module, and if the quotient ring is if the dimension of the ideal is equal to 0, then the saturation index as the saturation degree is just a inequality. And we can prove that for any graded idea, then we can prove the function, the saturation degree of I to the n is asymptotically either a constant or a linear function with a positive slope less than or equal to d, where d here is a saturation degree. D here is a asymptotic degree of I. So this function, this result hold for any graded idea, not necessarily equigenerate. And of course, we can go on to describe this saturation degree. We can give a completed description of this saturation of this function. But it will take a lot of time to describe about all these results.
Okay, well, you gave us some indication about what you've done on this, which is quite interesting. Does anybody have any questions or want to comment?
This is kind of a vague question, but these ideals that you constructed, have you like played around with them to see if they have other strange properties other than the defect sequence, but like, I don't know, like looking at the depth of R, and seeing what that sequence is, or something other than that.
Oh
Sorry.
no. First of all, that we would like to modify this construction to solve our problem. You can see that in the case where for the regulative function of the quotient ring or of the idea of the power of the idea, then there are still some case where we cannot give a complete description of the regulative function, and we can definitely say that this method, this kind of construction doesn't work. And now, of course, that now we concentrate our effort to study the polynomial case. So we don't think about other property of the idea of the power of the idea in our construction.
Makes sense. Thank you.
Any more questions? Well, let's thank Trung again, the speaker, and I guess that's the end of our meeting.
Thank you, Trung.
So I also would like to thank you all for just to participate to this seminar. It is a bit late in the evening. It's just maybe dinner time. For me, it is quite early in the morning. I have moved. I asked to move the time to 2 hours later than usual, because it is now 6-7 in the morning in Vietnam, and actually that I used to go to bed very late, usually that at 1 o'clock, at 1 a.m. So I would like to have a little sleep before my talk, and I'm really sorry that to move the time of the seminar to 2 hours later.
Quite all right, I think. Thank you for the nice, very nice talk.
Thank you.
Yes, thank you, Tim.
Yeah, thank you all. That I hope